So kind of the goal for right now for this lecture is more of a foreshadowing of things to come. We've talked about green serum, and green serum is this really beautiful idea in the plane. So you have a region in the plane, and you want to say, well, I can say something about the integral of some quote-unquote derivative over that region in the plane, and it would be the same as what I get for an integral of some related function on the boundary. What we'd like to do is we'd like to go to the third dimension. So to do that, we really need to understand surfaces. So today we're going to talk about surface integrals. Now, it should not come as a surprise what we're going to do, because we've talked about line integrals, and we've put them here side by side. So line integrals and surface integrals. Now, how do they work? Well, for line integrals, our idea was we have this curve, and we have some function that assigns values to every point in the curve. And we broke our curve into parts. So, for example, down here, we have our curve, and we can say, well, let's just take our curve and break it up into little tiny pieces and ask what's happening on each little piece. And once we know that, we can add those up, and that gives us our answer. For surface integrals, we're going to do something basically the same. The only thing that changes, instead of breaking a curve into parts, we break the surface into parts. So I have a surface here, and normally we think of the surface as z equals f of x, y. There are other kinds of surfaces out there, but this is the most common that we'll see. And downstairs we have our region R. So you can see that already it's been sort of chopped up. Of course, we can chop it up into even smaller parts if we wanted to. It doesn't really matter. The better we chop up, the better the approximation. And integration is all about what happens in the limit. So again, we break it up, what happens on each part, and we add the parts up. Now, where do we get the basic formulas from? Well, we start with what we know. So for line integrals, we said, I know how to find length. If I want to find the length of a curve, I integrate the x prime squared and y prime squared. And take this, the square root of that, and integrate. And we've done surface area. So for surface area, it's the square root of f sub x squared plus f sub y squared plus 1. Now you'll notice I am sort of suppressing some notation. So when I say f sub x, it's f sub x of x comma y and f sub y of x comma y. But I ran out of space. But you see the idea. And so finally, what do we get? Well, what's happening is we can think of this square root of x prime squared plus y prime squared. That's a small bit of arc length. So we call that ds. So if I want to integrate along the curve f of xy ds, what we do is we put everything in terms of our parameterization t. So everything gets updated. X and y becomes x of t, y of t. Our bound becomes alpha to beta. And our ds becomes this expression, square root of x prime squared plus y prime squared dt. So we're going to do the same thing for surface integrals. We're going to say, okay, I have this surface. And in particular, when we talk about the surface, again, thinking in terms of your z is f of xy over region R. So here we have our surface, and in case you're wondering what this symbol is, this is called fancy G. It looks kind of like an S, a fancy S, but it's a really fancy G. So anyways, so we have this surface, and we say, look, if I want to integrate on the surface, g of x of y of z dsa. Well, what does this part mean? Well, when I say d of sa, that's just shorthand notation for small bit of surface. So I usually like to think of the d as saying a small piece of. So dx, a small piece of x. Or arc length, ds, a small piece of length. So dsa just says I'm chopping up my surface into small pieces, a small bit of the surface. So that's dsa is this expression up here. So what do? We write everything in terms of an integral in terms of r. So we update. It becomes g of x of y, and I replace z by f of xy. And then my surface area, I use the surface area formula. Square root of f sub x squared plus f sub y squared plus 1 dA. Now at this point you can justifiably say, you got a square root here, Danger. Danger. Yes. Well, we'll find ways to get around that topic. But at the end of the day, the idea of surface integrals are fairly straightforward. Break your surface into parts, add up the pieces, and you get your answer. So let's do an example. Let's find the center of mass for our surface, and our surface is the shell of a hemisphere of radius 3. And particularly the hemisphere is the one that's above the xy plane. So when we're talking about the shell, it's sort of the candy coating of your M&M. It's not a solid hemisphere, it's just the surface. So if we were to look at this, we would have the following picture in mind. So there's my three-dimensional space, and I'm going to have here my base, and I can come up. And radius 3, so I go in 3 in each direction. All right, so there's our picture. And again, it's not a solid, it's just the very edge of the sphere. So we want to find the center of mass. Now, how do we go about finding the center of mass? That's a good idea. Do some quiet contemplation. Think about the center of mass. Well, by now you should hopefully say, it kind of should be like how we found center of mass before, and that's a good answer. Because the center of mass is always the same. I like to think of center of mass as being our weighted average. Now, there's a few things about this particular region that should stand out to us. Is there any symmetry involved in this shape?
Yes.
Yes. That's probably knew the answer just because I asked the question. In particular, if you look at the z-axis, we have rotational symmetry, which is to say if you spun it around, you get the same shape. Now, you have to be a little bit careful. Just because the shape is symmetric doesn't mean necessarily that the thing is fully symmetric. But notice that if I'm spinning around the z-axis, I don't change my density. All right, well, what does that allow us to conclude? Well, it allows us to conclude that the center of mass is on the z-axis. So if I can find any place where I have a rotational symmetry around an axis, the center of mass has to be there, which means that x bar and y bar are both 0. So that's good. That's 2/3 of the problem done. Wow, that was quick. I suspect the other third might be longer. So how do we go about the other third? Well, so we need to find our z bar. And for z bar, we say, well, look, that's found by taking a moment of something over the mass. Well, which moment? If I'm looking for z bar. Yeah, the moment we call m sub xy, which stands for the moment with respect to the xy plane. But really what it is you're going to add in an extra term, which is z for distance. So let's go through and do both of these integrals. So there's two integrals. So we'll talk about the mass. Now, if we're going to do this as a surface integral, because it is a surface, we need to know a couple of things. First off, we have to know what's our region. Because if you go back into our surface integral, our basic setup was we had a function, z of f equals f of xy, over some region R. So, where do we go? Well, the region, that's easy to spot. It's our region here in the xy plane, which is the bottom of the circle. So our region R is going to be a circle of radius 3. So that's good. Now, what about the sphere itself? Well, that's the formula, x squared plus y squared plus z squared equals r squared. Now, if you solve for z, z squared is 9 minus x squared minus y squared. And we take the square root. We want the top half of the circle, so we're using the positive part. If we had the negative, that would give us what's below the xy plane. So this part right here, this is our function f of xy. So our surface is z equals our function of f of xy over a circle of radius 3. So now we can start talking about our mass. So our mass is going to be the integral over our surface, and I'll call our surface G, of our density and times dSA. Now, one of the things that we should point out here is that I've made a terrible mistake on the previous slide, which I'm going to go through and correct right now. This should be a double integral. There we go. Now I feel better. Why should it be a double integral? Well, the question is, the number of integral signs gives you a clue about how many dimensions you have. And how many dimensions do we have? It's 2. A surface is 2-dimensional. A line is 1-dimensional. Okay, so we have 2 integrals, which means it's a 2-dimensional type thing to integrate. All right, well, let's see where we get to. So we need to find our d of SA. So let's do some side work here. So if I'm looking for d of SA, that's going to be the square root of f sub x squared plus f sub y squared plus 1 dA. That's our basic formula. And that's going to be the square root of. So we come down here and take our function f of xy, which we could write as 9 minus x squared minus y squared to the 1/2. And we take the derivative with respect to x. So that would be 1/2 9 minus x squared minus y squared to the minus 1/2 times negative 2x. So this is our f sub x squared. Then we do something similar for f sub y. And the really only difference for f sub y is that now it's going to be times negative 2y instead of negative 2x squared plus 1. Okay. And there's a dA that we can't quite fit. dA on the end. All right. Well, this is not looking promising. But it always looks darkest just before it goes completely black. So the 2's cancel. That's a little promising. When we square things, well, that might help a little bit. So really, what do we have? This is x squared. And now, when I square this term, it's going to become 9 minus x squared minus y squared to the minus 1, which becomes 9 minus x squared minus y squared downstairs. Similarly, the second term would be y squared, 9 minus x squared minus y squared, and then the plus 1, well, that's plus 1, which of course, common denominator, 9 minus x squared minus y squared, 9 minus x squared minus y squared, dA. Add these all together, and a beautiful thing happens in the numerator. You'll see the x squareds will cancel, the y squareds will cancel. So we're going to end up with the square root of 9, which is 3, over the square root of 9 minus x squared minus y squared dA. Okay, so there we go. There's hope. There's hope. That's not so bad. So now we're ready to tackle our mass. So what's our mass? It's going to be the integral over our surface. Our density is z dSA. And now this will become the integral over our region. Z becomes our function. That's the square root of 9 minus x squared minus y squared. dSA becomes 3 over square root of 9 minus x squared minus y squared, and dA. Well, what do you see? Cancellations. So, what are we left with? Well, the 3 can come out. That's 3 integral over our region dA. Now, we could integrate that, or we could be smart and say, hey, hold on a second. If I'm integrating over my region dA, that finds something. What does it find? This is the area of the region. So this is 3 times the area of R. Well, now I just come here and look at the geometry. Our R is a circle of radius 3. How much area is there in a circle of radius 3? 9 pi, pi r squared. So r equals 3, 9 pi. So I get 3 times 9 pi, which means my mass is 27 pi. Now, that's good news, because we now know the denominator. We're not done yet. We still have to do the m sub xy, which means we probably need another page.
So where did the z variable go in the bottom bit there? You have m equals z dsa, and then it disappears in the next step?
I don't know which one you're looking at. This here?
Yeah, that one.
It's right there. Z is square root of 9 minus x squared minus y squared.
All right.
Okay. So, time for the moment. Now, the good news is that the moment is really similar. It's the integral over our surface, a distance to the xy plane, which is z, times our density, which is z, times our bit of surface area. So we know what z is, so this will become integral over our region of square root 9 minus x squared minus y squared, that's z. I have two of them, so I'll just square that. The dsa is still the same, 3 square root of 9 minus x squared minus y squared, and dA. So, what do we end up with? Well, in this case, not everything does cancel out. So we get 3 over times the integral over our region of r of square root of 9 minus x squared minus y squared dA. And now, okay, is there a way to integrate this? Well, the answer is we're not going to. We're going to be smart. And we say, look, integrals have meaning. And regardless of where this integral came from, I can interpret this however I want. So let's think about an interpretation for what this integral could be. One thing you can always say is, you can think of an integral geometrically as saying I'm representing some sort of area, some sort of volume, so forth and so on. So if I'm integrating over a region, if I think of this as a height, what am I finding? Well, I'm finding a volume of a sphere. So if you integrate over region height, that's volume. So this integral here, I can think of as the volume of a hemisphere. Now, you might say, but wait a second, I thought this hemisphere, it was empty, it was just a shell. But you have to be careful here. I'm not saying that our hemisphere is solid. I'm just saying I can interpret this integral to be that. And then I'm perfectly fine. Now, this only helps us if we know how to find the volume of a hemisphere. Well, that's not bad. That's half of the volume of a sphere. And the volume of a sphere is 4/3 pi r cubed. In our case, our radius is 3, so 4/3 pi 3 cubed. Now, we can cancel a 3. We can also divide the 2 in here. And so what do we end up with? We end up with 54 pi, because I'll get 2 times 27. So that's our moment with respect to xy. That goes here, 54 pi. Well, 54 pi divided by 27 pi gives us 2, which means our center of mass is at 0, 0, 2. Well, we should always ask, is this a reasonable answer? Now, one thing is, it should somehow be more or less close to the center. Now, the good news is, 0, 0, 2, it'd be somewhere around here. And that says, all right, that's definitely convincing, because if it was 0, 0, 4, that's probably impossible, because it's impossible. Or if I got a negative number, also impossible. And we might say, well, okay, so it seems to be slightly biased towards the top, because it's height 3, and we're at 2. Should there be a bias towards the top? Well, yeah, there should be a bias towards the top, because we think about our density. It gets thicker the higher up we go. So we should expect there to be somewhat of a bias towards the top. So 0, 0, 2, that's a good, reasonable answer. All right, well, that's not so bad. Whew, thought I was going to not work out. All right. So that's a surface integral. Now, one thing that we're going to want to do, well, let's cover this up for a second, is talk about flux through a surface. Now, what do we mean when we talk about flux? Flux is, I think it's a Latin word, and it's just another word that means flow. So there's something that's flowing. Now, you can think of something that flows as a liquid. You can think of it as like wind blowing. You can think of it as electricity moving. Anything that has the ability to move. And so we tend to model these things with functions. So you have some function. We'll use capital F, and that's our flow. So it's a vector valued function. So at every point, we have a direction that things are moving and a rate, the amount that things are moving. So we want to measure how much is going through a particular surface. Now, one way to sort of think about what's happening here is you can imagine the following scenario where, let's see, my artist skills are somewhat poor, but suppose you had a little bit of a river, okay, indicated by the color blue, and that the water was flowing in a particular direction. And you wanted to measure how much flow is going through it. Well, at one point on the river, what you have is you have a set of sensors set up. And at the sensors, it's not a dam, so it's not restricting the flow of water, but it's measuring the flow of water. So I have these sensors here, and these sensors are telling me the direction that water is passing through at a certain point and the speed at which it's passing. So essentially the sensors here, these are reading off what the function f is. They lie on a surface. So the sensors are on some surface. And now what I want to do is I have this collection of data. So I have all this data. I know what's happening at each individual point, and I want to ask the question, what's the total? How much is there that's passing through? That's what we're after. So we have this surface, and we're asking ourselves the question, how much is flowing through this surface? And so what do? Well, we want to take the local information and add it up. Now, what do you do locally? So there's this idea that if I have a surface, so let's imagine I have some surface. So here's some surface down in space, or maybe up in space. I have, at a particular point, I can look at what's called the normal direction. So when I talk about the normal vector, that's something which is perpendicular to the surface. So why do we need the normal vector? Well, when I'm looking for an amount, I'm not looking for a vector. So the amount of flow it's going to be a number. So I need to convert that vector information about the flow into a number. So the way you do it to capture locally is you look at f dot n. Essentially what's happening here is you're taking the flow and you're projecting it onto how much is flowing at the surface. So that's a projection that's happening here. And so this f dot n is indicating how much is happening locally. So this is the local rate of flow. And now you want to say, well, wait a second. I want to find out the amount of flow. So I multiply it by this little bit of area. So rate at the local point times a little bit of area gives us the amount of flow locally. And finally, you add it up. So the flow through the surface is the integral over the surface, f dot n d of SA. Now, at this point, we're feeling like maybe we're getting lost in a little bit of alphabet soup, because there's all these symbols here, and it's getting more and more convoluted. So what we want to do is really say, okay, let's just break it down. How do we actually do it? What do we do to find the flow? So we need to go, and we're going to work through a special case. So we're going to go through the special case. Our surface is the kind we've been talking about. Our surface is z equals f of x, y. So I want to talk about the normal vector. How do we find it? So now we go back to an earlier part of the class and said, well, how do you find a vector which is perpendicular to your surface? And the answer to that is you use the gradient. The gradient vector is perpendicular to your surface. So if I'm looking for something which is perpendicular, I'll take my surface, I'll write it as the form z minus f of xy, take the gradient. This resulting vector, it's guaranteed to be perpendicular to the surface. It's not quite the normal vector we need, but it's perpendicular and it points in the right way. I guess I should also add, when I say points in the right way, we have to make a choice. We oftentimes, we sort of default to upward pointing, and what's our choice? We're going to surfaces in three-dimensional space. So our choice is how do we stand on the surface? Because I can take this surface and I could stand on one side and I could say, yes, I'm on the top of the surface. But of course, I could have also stood underneath it and said, well, no, the top of the surface is on the other side. So you have to make a choice as to what surface is on top. Now, whenever you hear this, you have to make a choice. What you're really talking about is orientation. So surfaces have an orientation, and we have to respect the orientation. All right, so there are actually two vectors you could have used. This vector, which is minus fx minus fy1. The other one is fx fy negative 1. That would be if I want it to be downward pointing. The key is to go off the third entry. The third entry is either positive, which means you point up, or it's negative, which means you point down. So finally, you make it into a unit vector. You take the length 1, make it length 1, divide by its magnitude. And you might say, this looks suspiciously familiar, as though we've seen it earlier today, because we have. And that's going to be to our advantage. All right, so here we go. We combine everything together. So if we want to find the flux, which means you're computing the integral of f dot n dsa, then we just put everything we have. F is our vector valued function, which we write as mnp. N is the normal vector, and we're going to do upward normals. We even specify which way we point, upward. And then our DSA we write as we had before. And now comes the beautiful part. The square roots cancel. That's good news for us. Since the square roots cancel, what's left? Well, the vector valued function dot this expression. So it becomes minus mfx minus nfy plus p. So this is the formula to remember. So if you see anything asking for flow or for flux, this is the formula you should think of. That's what you're computing. Now, just to sort of get some orientation here, this is the surface we saw before. These green vectors here are the n. So they point perpendicular. You can see that as my surface starts to warp, they do change the direction they point, which is because as the surface changes, your normal vectors also have to change. All right. So I guess the two big takeaways for today are how do you do surface integrals? And as a special case, let's talk about flux through a surface. So let's do some examples. Any questions, I guess I should ask? This is a little bit more abstract than usual, but examples will probably help. Okay. Find the flux for the function, vector valued function, xi plus yj plus zk, for the surface with an upward pointing normal, given by z equals 1 minus x squared minus y squared above the xy plane. So probably we should understand a few things. Let's start with this surface. Do we know what this looks like? Z equals 1 minus x squared minus y squared. It's not quite a sphere. If it was z squared equals 1 minus x squared minus y squared, that would be a sphere. What if we said the following? Suppose I just said z equals x squared plus y squared. Do we know what that looks like? Well, it's a paraboloid. Or, if you're not being very fancy, it's a bowl. So that's a bowl. Suppose I now make it minus x squared minus y squared. What does that do to my bowl? What? Flips it upside down. So now my bowl's down here. Okay. Now I add 1 to it. What does that do to my bowl? Shifts it up. Yeah, shifts it up in the z direction. So now here's 1, and it goes down. And it keeps going down forever. Now, we don't want the whole surface. We said we just want part of the surface. We want the part of the surface above the xy plane, which means that we're going to stop this at the point where we're above the xy plane. So yes, even though our surface goes down for a very long time, we don't need that part. We just need this part. So let's talk about, well, what do we need? We have our function. So we already have our f of xy. That's the 1 minus x squared minus y squared. That's our f of xy. Do we know our region? Well, what is our region? The unit circle. So the question is, where do I hit the xy plane? I hit the xy plane when z is 0. So I'm at the xy plane, z equals 0. That means that 1 minus x squared minus y squared is equal to 0, or x squared plus y squared equals 1. So this right here says that our r is the unit circle, the whole circle, not just the edge, the whole circle. Okay, so we have our function, we have our region. So now we can apply the formula. So the formula says you're going to integrate over your region minus m times fx minus n fy plus p. And one of the things that we should note here is you might have expressions of z in here. And if you do have any expressions of z, update the z. And the way you update the z is you replace it by whatever your function f of xy is. That might not arise in this situation, but if it does, we know how to update it. So your integral should be entirely in terms of x and y. There should be no z's left over. So let's see where we go. So we're going to have our flux is the integral over our region of minus m fx minus n fy plus p dz. dA. Now I'm just writing down the generic formula. So when we talk about m and p, that's these pieces here. M is x, n is y, and p is z. So this becomes the integral over our region of minus m, that's going to be x, times f sub x. Well, what do we get when we take the derivative of f with respect to x? Minus 2x. Minus n, so that's minus times y, times f sub y. What do we get when we take the derivative with respect to y? Minus 2y. Plus p, which is z. Well, but we don't want z, we want everything in terms of x and y. So, instead of writing z, we replace z by 1 minus x squared minus y squared. And this is our integral that we're going to work out. Okay, well, let's see what this becomes. So this becomes the integral over our region. Here we're going to get 2x squared plus 2y squared. But then we also have a minus x squared and a minus y squared. So it becomes x squared plus y squared plus 1. Now, how do we actually go about doing this integral? Here we can't just fall back on geometry, unfortunately, but what can we do? We can do polar. Now, polar is a good choice because we see a unit circle. So if we keep it going here, this will become the integral x squared plus y squared plus 1 will become r squared plus 1. dA becomes r d theta. Theta goes from 0 to 2 pi, and r goes from 0 to 1. So this is integral. We can actually pull this one apart. 0 to 2 pi d theta. Integral 0 to 1, r cubed plus r dr. So the integral from 0 to 2 pi d theta is 2 pi. We see that a lot. Integral of r cubed plus r, 1/4 r to the 4th, plus 1/2 r squared. Evaluate from 0 to 1. And we'll end up with 1/4 plus 1/2, which is 3/4. 2 pi times 3/4 gives us a final answer of 3 pi over 2. So that's the amount that's going through the surface for that particular type of flow. Okay, good. Well, let's do another one. So I guess this equals equals 3 pi over 2. Find the flux for 3y x6 for another surface, f of xy, which is x plus 3y squared minus xy, with downward pointing normals over 0 less than or equal to x, and 0 less than or equal to, 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to 1. So if we're talking about our flux, so let's think about what the change is. So I have the normal flux. What does the downward, what effect will I end up with? It changes the sign. So downward is about orientation change. So the easiest way to fix an orientation change is just throw a negative in front. So, but then everything else stays the same. So minus the integral over your region, r of minus m fx minus n fy plus p. Everything else stays the same. Okay. Now here we can see what m, n, and p are. They're given to us. It's actually more straightforward because there's no z's floating around. And, well, let's see where we go. So if we throw the integrals, the minus signs past the integral. So we're going to get the integral over our region of m, which is 3y, times f sub x. Well, what is f sub x? 1 minus y. Then minus makes this a plus n, which is x. And then I have f sub y. Well, what is f sub y? 6y minus x. And then finally I have minus p, so that'll be minus 6 dA. And our region is actually a really simple one. It's a square. So integral 0 to 1, integral 0 to 1. We'd multiply it out, 3y minus 3y squared plus 6xy minus x squared and minus 6. And at this point, you say, well, this is now just sort of a calculus 1 problem. And it is. And if you go through and work it out, you'll see, let's see, the first part, you'll end up getting a contribution of 3/2. The second part will end up being -1. Here you'll get 6/4, which is 3/2 again. This will be a minus 1/3, and that'll be a minus 6. And so whatever that turns out to be. I'm going to skip the steps because I want to talk about one more thing. One more idea. Last idea. Well, what we've talked about works great if we have some very special types of surfaces. So in particular, when we have surfaces that we can write in the format or have some region downstairs, here's my R, and then upstairs I say, okay, well look, there's some surface that's above here. This is my z is f of xy. So for these we can do now our surface integrals. But not every surface can be written in this way. So as in a very special case, a surface that we'll probably see from time to time, let's just take a cylinder. If I look at the cylinder here, it's a very simple surface. It's just take a circle and extend it. But you can't write this as z equals a function of x and y. The problem is that you can see the surface extends up and down over a point. And you might say, well, maybe I just should switch. Maybe instead I should write as x as a function of y and z. You could do that, but now you still run into the problem. You'd have to break your surface into several parts. So this is sort of an inconvenient thing to do. We'd like to do something that's a little bit cleaner. So here's the idea, is to say, well, how can we handle that? And here's an analogy. So think about what happened when we had, just in the xy plane, we'd have a circle. And we said, well, look, you can't write this as y is a function of x. But what you can do, and what we did a lot, is we said, let's parameterize. See, parameterization allows you to repeat the same x coordinates or the same y coordinates. And so we were able to get a circle in a very clean way as a parameterization. So we can parameterize lines, but good news, it's also the case that you can parameterize surfaces. So what does that mean? Well, what this means is I have here some region. Say this is my region here, R. And this is in the UV space. And I can map it into three-dimensional space. And maybe this can become a cylinder. All right. So in other words, I can transform something in the UV plane, a region, into a three-dimensional setting where I couldn't cleanly do it if I was just trying to z as a function of x and y. And the way you do it is you say, for every point that you start off over here, there's a corresponding point on the surface. So it's essentially a mapping. How do you go from that region and get to your surface? So you have a function, we like to call that r. And it says, okay, if I'm at a point uv, where am I at in the corresponding surface? Now, there are several questions, one of which I'll just point out really quickly on the bottom. Oh, are we going to be tested on this? No. Should you know it? Well, I think you should at least be aware of it. It's a really beautiful idea. Well, you should know that we can do these things. So the question becomes, well, how do we find things? Well, if you go back to what we did when we talked about finding the Jacobian, one of the things we said is, suppose I want to take a little piece here and find how big is that corresponding piece over there. And the way you do it is you take the cross product of the r sub u and r sub v. That's essentially doing that parallelogram, and you find the magnitude of it. So you can figure out how much does the little surface piece match the little piece over here where you came from. And once you have that, then now you can do surface integrals with parameterized surfaces. You write everything in terms of u and v. So x, y, and z become everything in terms of u and v. So the corresponding x of u and v, y u and v, z u and v. dsa becomes that magnitude of that cross product. And you integrate over region R. And this R here, this is in the UV plane. So to give some idea of what's happening here is, suppose you have a cylinder of radius 1 and height 1 sitting on the xy plane. This can be parameterized in the following way. Cosine u, sine u, v, where u goes between 0 and 2 pi, and v goes between 0 and 1. In other words, there really is a nice parameterization that takes us from this surface, or this region here in the UV plane, onto a cylinder. And now it says, well, suppose I want to find the mass and I know the density. The density is given by 1 plus x squared z, and I want to determine its mass. Well, how do we do it? Now, the way we do it is we set it up. So you have to know a few things. First off, you have to look at what is r sub u. And if you look at r sub u, you take the derivative with respect to u. That's minus sine u, cosine u, and 0. You have to look at r sub v, which is 0, 0, 1. And then you have to look at the magnitude of ru cross rv. And if you work it out, you'll see it turns out to be 1. So the integral over our surface of our density function dSA, well, that would become the integral over our region in the UV plane, this region here, of what? Well, 1 plus x squared. X will be cosine squared u. Z is v. And then times magnitude of RU RV, which is 1 times du dv. Okay, and you can work that out. We're almost out of time. You might say, wouldn't it be simpler to think of it in the following way? As if, well, I want to understand what's happening in the cylinder. Couldn't I just pull out a pair of scissors and cut along one edge of the cylinder and lay it flat? That seems to be simpler. But actually, that is what's happening. It's just sort of a way to represent things. Okay, last example. You've recently been hired to help design rides in an amusement park. That sounds like a pretty good job. Now, one of the rides that you are working on involves a large saddle-like surface on which people will be strewn into. In particular, the surface is z equals x squared minus y squared, where we have 0 less than or equal to x squared plus y squared less than or equal to 4. So, some sort of saddle-like shape. Something looking roughly like that. Okay, so here, this is our surface. Z equals x squared minus y squared. That's our f of x, y. And then this, at 0 less than or equal to x squared plus y squared less than or equal to 4, this is our region R. In particular, it's a circle of radius 2. Okay, so there we go. So we have our surface, we have our region, our surface is over, and what's happening? Well, we want to make sure there's enough supports in place to support the structure, because it definitely, if it's going to have people on it, we want to make sure it doesn't collapse. The design calls for the density to increase with distance from the middle. So, in particular, the further we're out from the center, the more dense we are. So it's very not dense at the center. So if we look at our saddle here, it'll be very not dense near the center, but as you move towards the edges, the density increases. And the question is, what's the total mass? Okay, so what do we need? Well, the mass is going to be the integral over our surface of our density dSA. Okay, so how do we compute this? Well, we need to get a handle on what is dSA. So what is that? Well, this is the integral over our surface, density x squared plus y squared. And d of SA, what is that? For that, we say this will be the square root of f sub x squared plus f sub y squared plus 1. So for us, our f sub x, f sub y, that becomes the square root of 2x squared plus negative 2y squared plus 1. And so we get the square root of 4 times x squared plus y squared plus 1 dA. Okay, so let's see where we get. So this is going to be the integral over our region of x squared plus y squared times the square root of 4 times x squared plus y squared plus 1 dA. Now, our region, being a circle, that should be a polar coordinate. So let's switch to polar. So we're going to go 0 to 2 pi, 0 to 2. Everywhere we see x squared plus y squared becomes r squared. So square root of 4 r squared plus 1. And of course, dA is r dr d theta. We can pull out the d theta integral separately, do that really quick. 0 to 2 pi d theta, 2 pi Well, that was easy. The other one I suspect we'll have to think a little bit about. So this is 0 to 2, and we're going to have r squared, square root of 4r squared plus 1, and r dr. Now, what do we do? Well, we're set up to do a good substitution. So if you set u equal to 4r squared plus 1, then we get that du is 8r dr, or 1/8 du is r dr. So that will handle the r dr. And then you have the r squared. Well, you can say that u minus 1 over 4 is r squared. So we can handle that. That's something we can work with. So what do we get? Well, integral 1, because we have plug in r equals 0, and then 2, well, 4 times 4 plus 1 is 17. And then we get the following. R squared becomes u minus 1 over 4. Square root of 4r squared plus 1, u to the half. And r dr is 1/8 du. So this is 1 over 32 times the integral from 1 to 17, u to the 3/2 minus u to the 1/2 du. And that is 1 over 32 times, then we get, well, we raise things up, that'll be 2/5 u to the 5/2 minus 2/3 u to the 3/2 evaluated from 1 to 17. Well, what do you do? Well, we put everything together. So our final answer, if we don't worry about simplifying, is we get a 2 pi. Then you have a 1 over 32. So that's pi over 16 times, plug in your 17. So that's 2/5, 17 to the 5/2 minus 2/3, 17 to the 3/2, and then subtract, plug in 1. Well, plug in 1, it's easy, 2/5 and 2/3. So minus 2/5 and minus minus makes plus 2/3. And there you go. That's the mass. All right. Well, maybe it's not the most elegant answer, but it's an answer. We can find it. So that's good. All right. We're done.